Welcome to our quantum deep dive. We take complex stuff and, well, try to make sense of it.
Make it digestible.
Exactly. Imagine a universe just empty. No stars, no planets, definitely no us.
Which is kind of what our best physics theories said should have happened right after the Big Bang.
Right. So today, we're diving into why it didn't happen that way. Why matter somehow won out over antimatter.
This cosmic imbalance that fundamentally allows everything we see to exist.
And we're drawing heavily on Jörg O. Schneppet's fantastic essay, Baryogenesis Ursprung der Materie im Universum.
It's a core mystery. I mean, look around. Everything you see, touch, it's all matter.
Yeah, totally dominated by matter.
Yet quantum field theory, our rule book for fundamental particles, predicts the Big Bang should have made exactly equal amounts of matter and antimatter, perfectly balanced.
Okay, hold on. If it was perfectly equal, wouldn't they just, find each other and poof, annihilate?
Precisely. Total annihilation. You just have a universe filled with radiation, light, basically. No stable structures could ever form.
No stars, no galaxies.
Yeah. No us. But thankfully, that's not what happened. We know from really precise measurements, especially of the cosmic microwave background radiation.
The echo of the Big Bang.
Exactly. Those measurements show there was a tiny, tiny leftover bit of matter. For every billion pairs of matter and antimatter particles that annihilated, just one single matter particle, like a proton or neutron, a baryon, survived.
1 in a billion. That sounds incredibly small.
It is. Quantified, it's a baryon to photon ratio around 6 × 10 to the -10. Almost nothing.
But that almost nothing is literally everything.
It's the reason anything exists. So the big question is, how did that happen?
Yeah, what allows that tiny imbalance?
Well, back in the 70s, the physicist Andrei Sakharov figured out you need 3 specific conditions. They're now called the Sakharov conditions.
Okay.
First, you need processes that violate baryon number, basically ways to create or destroy baryons to change the count. It can't be a perfectly conserved quantity always.
So the rules have to be bendable sometimes.
Okay.
Got it. What's second?
Second, you need something called CP symmetry violation. This is crucial. It means the laws of physics aren't exactly the same for matter and antimatter.
So they have to behave slightly differently. There needs to be some bias.
A preference, exactly. We have actually observed this CP violation in particle physics experiments, like with particles called kaons and B mesons.
Right, I've heard about that. So the standard model includes some CP violation.
It does, yes. But here's the catch. The amount we've measured in the standard model is nowhere near enough. It's way too small to explain that 1 in a billion leftover matter.
Okay, so our best theory is incomplete on this.
Fundamentally incomplete. It points directly towards needing new physics beyond the standard model. And Sakharov's third condition.
What's the left piece?
Thermal disequilibrium. The very early universe couldn't have been in perfect thermal balance. It needed to be out of equilibrium for this matter-antimatter asymmetry to get locked in or freeze out and not just get washed away later.
Okay, 3 conditions. Bend the baryon rules, break CP symmetry significantly, and be out of thermal equilibrium. And the standard model fails on number 2, mostly.
It fails to provide enough CP violation, yeah. Which pushes us to look for new theories.
So what are the leading contenders then? What theories go beyond the standard model here?
Well, 2 big ideas are often discussed. One is called electroweak baryogenesis. It connects the matter asymmetry to the electroweak phase transition in the early universe, tied up with how particles got mass via the Higgs field.
Okay, linking it to the Higgs.
Yeah.
Interesting. What's the other one?
The other popular idea is leptogenesis. This suggests the asymmetry started not with baryons, but with leptons, particles like electrons and neutrinos.
An imbalance in neutrinos first. How does that help?
The idea is that an initial lepton asymmetry gets converted into the baryon asymmetry we see today. This often involves hypothetical heavy neutrinos and a concept called the seesaw mechanism.
The seesaw. That also explains why the neutrinos we do see are so incredibly light.
Exactly. It's an elegant theoretical connection. 2 puzzles potentially solved with 1 mechanism.
So how are we actually testing these ideas? These sound like conditions from the universe's first tiny fraction of a second.
It's tough, but we're pushing hard. Experiments at the Large Hadron Collider, like LHDB, are making ever more precise measurements of CP violation, searching for any tiny deviation from the standard model's predictions.
Looking for that missing piece.
And we keep looking at the cosmic microwave background for confirmation of the overall asymmetry value. Plus, huge efforts are going into neutrino experiments.
Like Dione and Hyperkamiokande.
Yes. They're designed to search for CP violation in the neutrino sector itself. Finding that would be massive support for leptogenesis.
It feels like this is where quantum technology really starts to play a role, too.
Oh, absolutely. Baryogenesis is fundamentally a quantum field theory problem. And simulating these theories, especially the nonlinear stuff, possibly involving things called sphelerons.
Sphelerons, what are they?
Think of them as sort of theoretical doorways in quantum fields that might allow baryon number violation. Very complex to model.
Too complex for normal computers.
Often, yes. That's where quantum computers could be game-changing, potentially allowing us to simulate these early universe processes directly.
And what about detecting things? Quantum sensors.
Definitely. Things like advanced atom interferometers are being developed for extreme precision measurements. They might be sensitive enough to pick up tiny, subtle effects related to CP violation or other new physics needed for baryogenesis.
So new ways to simulate and new ways to measure.
Right. We're also seeing innovation in things like squee-wides, ultra-sensitive magnetic field detectors, and optical atomic clocks, pushing measurement precision constantly. The hunt for baryogenesis drives technology.
So this baryon asymmetry problem, it's still one of the biggest unanswered questions, really highlighting that the standard model isn't the final word.
Not by a long shot. And future research will keep exploring broader ideas like grand unified theories, maybe supersymmetry, or even connections between baryogenesis and dark matter.
And new experiments searching for things like proton decay, plus these next-gen neutrino detectors, combined with quantum tech. Feels like we're getting closer.
We hope so. It's a long road, but the potential payoff is understanding our own existence.
It really boils down to that, doesn't it? Why are we here? Without this tiny, specific imbalance, the universe would just be radiation soup. Featureless.
A profound thought. The universe is stranger and perhaps more finely tuned than we often realize.
Well, that's our deep dive for today into the origin of matter. A huge thank you for joining us.
Always fascinating.
And if you want to explore this topic further, we really recommend checking out Jurgo Schneppat's work. You can find it at schnepppat.de. Thanks for listening.